Well, thank you. Thank you for the opportunity to present here. So my name is Lennart van Heijen. I work for a company called GreenFlux. And in the past 3 years, I worked as project leader for the Electric Nation project. And I will tell you a bit more about that today. We at GreenFlux, we have the vision. We started the company because we wanted to enable driving on complete renewable energy for all electric vehicles. And though this sounds nice, this is actually quite complicated if you go into all the technicalities. And this project contributed a little bit to that. Just to give you a very short background on what we do, we are a white label platform provider. We currently have 20,000 charge stations connected, though we as GreenFlux don't have any charging stations ourselves. So these are the charging stations of our customers. Our customers use our technology in different areas of the world. Actually, I asked our marketing team to update this because Australia and Brazil are missing at the moment. And currently 61,000 drivers are making use of our technology. And through a roaming agreement, these drivers have access to over 100,000 charging stations. And there are over 1 million EV drivers that can use our customers' charging stations. So we're going somewhere at the moment. This is just a quick overview of what our customers do with our platform. So we do the billing and transaction management. So that's if charging stations are used, that this is actually invoiced to end customers and that somebody is being paid for this. Remote management and support, the global roaming, of course, smart charging, which is the topic of today. We provide a white label app, and we have a lot of interfaces to interface with existing systems. For instance, interface with CRM systems of our customers. But I won't give you a full presentation of the GreenFlux system because we will talk about smart charging today and specifically the Electric Nation project. But to start off with smart charging, what it is, in essence, it's very, very simple. All we do is increase or decrease the maximum charge rate for an electric vehicle. There's an important nuance there. This means that we cannot set the exact charge rate of an electric vehicle. We can only set the maximum. So it's not possible to tell an electric vehicle you have to charge at 12 amps because it will be very dangerous, because if the battery is already full and we force it to charge, then it will actually explode. So this is of course not allowed. So we can only set the maximum charge rate, but we can work with it. The more interesting question is, why would you do smart charging? There are basically 4 reasons for this. And I've been giving these presentations for 10 years now, and nobody's corrected me so far on this, so I assume this is correct. 4 reasons. So the first of them being grid constraints, and these could be any grid constraints. It could be the grid of the transmission system operator, could be a distribution transforming station, a low voltage transformer, a low voltage cable, but very, very often in our case, it's the circuit breaker inside a parking garage or the circuit breaker of a building where some electric vehicles are connected to. And we see currently that this is also the biggest business case at the moment for smart charging. I'll talk a little bit about that later. Next reason is that energy prices are not constant, and that we have different energy prices in 6 or 7 different markets. It depends a little bit on the country you're in, which you can make use of. So you play around with when to charge an electric vehicle, and actually a lot of money is to be made. The business case here is not so big yet, due to the fact that that this becomes interesting when you do this with several thousand charging stations at once. There are not many parties that have several thousand charge stations in their portfolio, let alone that those charge stations are all able to do smart charging. But this is what we expect to become very big in the next year or 2 years. This is what we're ramping up towards. Of course, you need to take into account user requirements. You cannot postpone somebody's charging for 48 hours. I'll talk about that as well today. And finally, there's the renewable energy locally produced that you might want to take into account. This is always a bit of a strange one because local renewable energy has 2 effects. It has an effect on the grid load. It has an effect on the energy balance. So basically, we already covered them in the grid constraints and dynamic energy prices. So it's a little bit up to the local legislation whether or not this is interesting. So if the feed-in tariff is exactly the same as you pay for the electricity, then there's really no incentive to charge on local renewable energy. But for instance, in Germany, if you have solar panels on the roof, you are not allowed to feed back more than 80% of its maximum power back to the grid. So there's a very strong incentive to take into account local renewable energy. But in fact, it's not so much different from taking into account grid constraints. How we do this is a little bit different than most of our competitors. What we see mostly with smart charging is that you have a local network of charging stations of the same brand connected together via an Ethernet cable or an RS485 cable. And there's a proprietary protocol, and this works okay. And this is usually done, if you go back one slide, to take into account the grid constraints. So the circuit breakers are not overloaded. It's not possible in this way to take into account dynamic energy prices or user requirements, because the user cannot communicate with such a local system. And it's also a little bit tricky that you have a complete vendor lock-in with one of those manufacturers. Because if this manufacturer goes bankrupt or another one is cheaper, then you cannot connect several chargers to the same local system. Which is why, and which is actually the reason why we were asked to give this presentation, which is why we do all smart charging via OCPP. This works very well. It's not that easy actually, but it works very well. The big benefit is that we can do it with any charger around that is smart enough. And that's, well, we can take into account all these four relevant aspects that I mentioned before. So we quickly go over this. It's the good thing, it's infinitely scalable. Of course, in reality, nothing is infinite, but well, we can scale it as high as you want. Basically, it's just installing more server capacity. Works with any charge station. You can take into account any inputs, and very important, it's part of an ecosystem. So we can, if there are new interfaces to be made or relevant inputs that we could use, we can always do this because we do everything from the cloud, which is much more flexible than any other system. And then, of course, how we do it. As I said, in essence, smart charging is simple. Later on, I'll tell you why it's not so simple, but in essence, it's simple. Very often we have a maximum which we need to comply with, which we cannot reach. And very often this maximum is fixed because it's simply a circuit breaker in a parking lot. It doesn't need to be. Well, I present here time and power on the axis. If you multiply those, time and power yields energy. So this, what you see here, is a little block of energy, specifically a block of 50 minutes with some power.
Lennart, sorry to interrupt you. Sometimes your voice is going low. Maybe you could speak closer to the microphone if you don't mind.
That's really close to my mouth.
All right, okay. Yeah. Just wanted to let you know that sometimes your voice is fading a bit.
Okay, I can take away the microphone, and let me try that, and I'll take it away and I'll see if the laptop sound is better. Just let me know. Is this better? Can you still hear me? Miriam, can you hear me now?
Yeah, yes, I can hear you.
Okay, that's good. So if you have this block of energy and you start charging and stacking those blocks, then this obviously is what you want to prevent. And this is basically the solution. Just swap these blocks around. So in essence, smart charging is really not that hard. You can also do this dynamically. So I mentioned this red line in this graph here can be dynamic. And this was actually a test that we did for the smart charging project and the Electric Nation project. So this was on a test location. And you see here that this line, the maximum, is changing over time. And this was just made up randomly. This was a test. But it could, for instance, be that here during lunchtime that the kitchen is using all the energy in the building. And this is why all the electric vehicles need to be ramped down. You see here that it's nicely, these are real results. Put into Excel, I'll admit that, but these are real results. And you see also here that there's different types of electric vehicles with different maxima. For instance, Mitsubishi Outlander cannot take more than 16 amps and it has a smaller block, while a Kia Soul can take 32 amps and it has a larger block. So this is basically what we do. And just to give an example, this is the head office of Enexis, a Dutch grid operator where actually I used to work myself, where we increased the number of chargers from 16 in 2013 to hundreds in 2018. And these are all 32 amp charging sockets. So 100 chargers at 32 amps would mean 3,200 amps. And well, the investments to realize this are enormous. You need to add extra transformers in the basement. They don't fit there. You have to break down bearing walls with the entire building on top of it. And this was calculated to be roughly €250,000. Well, in fact, there was 400 amps available. So we completely saved all the capital expenditures. So the only cost that needed to be made were the charges itself. And also the annual added costs for this high grid connection are also saved. But this is why there's a very large business case. It's not that easy to make €250,000 with energy trading with 100 charging stations. But they don't need to be mutually exclusive. You can do both at the same time. Very important to realize is even in this situation, we only intervene with smart charging about 10% of the time. So the quickest solution would be, well, just limit each charger not to 32 amps, but to 16 amp or to 12 amps. But we don't do that because we only intervene 10% of the time, which means that 90% of the time, the chargers can charge at full capacity. And this is a very important point to make. Smart charging does not slow down your charging. It actually makes charging faster. So even though you preserve the grid constraints, the end user will benefit from it because on average, he has a 90% higher charge rate. Now, so far for the introduction, let's go to the Electric Nation project, which is, to my knowledge, the largest smart charging project ever done in the world. It consisted of 673 participants, lasted for 2 years, but to give you an idea how difficult it is, it took 4 people 1 year to recruit these 673 participants, after which this trial started. And as you can see from this map, they were spread out all over the UK. Well, not all over the UK, but all over England, which can only be done if you do this via OCPP. If you do this with a local solution, then of course you cannot put cables throughout the entire nation. We're over 130,000 charging events. And the great thing about being part of this project, we were the technology provider of this project, is that we had a lot of hypotheses that we thought were true, but this was finally the chance to prove them on a large enough statistically relevant set. So there's very interesting results coming from this project. Now in Ascension, in essence, it's more or less the same as we did in this Annexus building. So this is a picture which could have been the consumption by the office building. So there's some peak by the office building, and it's not that much different whether it could be a peak by an office building or the consumption by households. This actually is the consumption by households. So what we did there, we measured the transformer, flipped this upside down, and then what you have below here is the spare capacity that's available for electric vehicles. Everything in this pilot, let me skip back here, everything here was real. So the chargers were real, the electric vehicles were real, the smart charging was real, locations were real, the cars were real, the people were real, the issues we had were very, very real. The only thing in the transformer station we based this on was real. The only thing we simulated is that we pretended all these red dots to be behind one transformer station. And this was necessary because there is no location in the world where you have this many electric vehicles behind one transformer station. So this is the only part that was simulated. So we pretended all those chargers to be behind one transformer station. And this transformer station had the consumption as shown over here. And then we allocate energy to electric vehicles, which is left over on the transformer station. This is still an example, and this is real data again. So here you have this black line, which was sent to us by Western Power Distribution, saying this is the amount of capacity that you can use. Whatever you do, we don't really care, but stay below this line. Otherwise, this, with the addition of the household consumption, will overload the transformer station. And we just started doing exactly what I showed you again. We started handing out packages of energy, in this case, every 15 minutes. Not sure if you can see my mouse, but at 6:45 p.m., there's this green block on the top starting, and you can see this is 32 amp. Next block is 32 amp. Then there's nothing there, so it has been paused for a while. Continuous charging, then it's ramped down a little bit at 8:15. And then somewhere close to 10 o'clock, it's full. And we allocate just a low capacity, just say, for instance, he wants to have heating and use power for that or whatever. And you see that this works very well. You can also see that if you would do classical insulation technology, say this is a building, then an installer would say, well, I don't have this much capacity left, which you want to use. And I would not be able to charge those cars if you do it in a classical way. So here immediately from real life data, you can see the benefits of smart charging. I can charge more cars on the same network and actually have a lot of capacity to spare, because I think the white area under the line is more or less the same, well, maybe a little bit closer, maybe a little bit less than the colored area. So we could even add more cars here. we did 3 iterations. It was a 3-year project, so we did 3 iterations. So this basically was the first iteration we showed. We just started it and just let it run. People were asked to join, and they got a free charger to join. And then, well, they had coming what was coming to them, and we just managed their charging. They had no influence over it. In the second iteration, we did more or less the same, but we introduced an app, a user app. And with this app came a new function, became the high priority function. So basically had 3 levels: medium priority, just normal charge, and low priority if you're nearly full or already full, and a high priority, which you could request with one simple button, a high priority button. And this worked really, really well. So the interesting thing was we were not the only technology provider. There was a second one, and the other one had a more complicated app. We're very happy with that because this was one of our hypotheses. The complicated app asked people when they were going to leave, how far their next trip was, how much energy they would need, and information like that. And nobody used this because it's simply too much hassle. People don't want to go through the trouble of entering all this information, which was what we thought. We'd never been able to prove, but now we did, and people did not use that app, and they did use the high priority button. And in the third iteration, we introduced price incentives. So we said, well, if you charge at a cheap moment, then for each kilowatt hour that you charge, you get some money. And if you don't look at cheap moments, you'll lose some money. I'll explain that in a bit more detail. So these people all had different energy suppliers, and we would not be able to convince 700 people to switch energy supplier just for this project. So we did not include the energy providers in the project because it would be undoable. So what we did instead of that, we said, well, we'll have this energy rates which hold for everybody, regardless of the energy provider. So on average, you set a 50 pence unit fixed price tariff. Each kilowatt hour that you charge at a moment that the price is lower, you gain some money. And each kilowatt hour that you charge from, in this case, 1630 to, what is it, 8 o'clock, you will lose some money because that's the expensive part. You could select this via this app. The charging, well, as you see there in the red circle, we have the minimize cost option. And very important, this was the default option. We know from earlier projects that people very often stick to the default option. And the default option basically said, well, I don't care about these price incentives, just charge me whenever I want. We saw a lot of people changing actually, so that this was a good incentive, even though this was a default. So there were 3 options. Oh, sorry, this was the default setting. I said it wrong. This is the default setting. This is the optimized time. Basically say, whenever I plug in, just charge me. You had the minimize cost option. It says, well, if I start charging in the time range between 1630 and 22 hours, then the charging will be postponed until 10 o'clock. And if at any other time I'll plug in, I'll charge. But say, for instance, you would start a charge session at 4 o'clock, then it would charge for half an hour and then stop charging. And then continue again at 10 o'clock. And there's the somewhat in the middle, so optimize time and cost. So don't charge at the highest rate, but if it's a little bit more expensive, then we can charge as well. So you see here on the app side, you see all these different charge sessions, how much energy was charged, and some have a minus sign, some have no sign. Actually, this was a test app. And at the end of the project, well, this was make up money because this was not actual energy tariff. But at the end of the project, the award was paid out in the form of an Amazon voucher. And I think on average, people made like 15 or 20 pounds, but the people that did best, they scored up to 80 pounds. So this is what we did. I've been saying a lot that smart charging is easy. And this is actually why it's not that easy. So several reasons. After this, I'll skip to the results. I'll switch to the results of the project. This is what we learned why it's quite hard actually. It's crucial to have enough data for smart charging. And there's a lot of data that you would want to have, but you simply don't have. There's a lot of university papers written on how to do smart charging, and they all assume the state of charge of the vehicle to be known. They assume that they know when a car is going to arrive, when a car is going to leave, how much energy the next trip will need, and this data is simply not available. So you have to come up with algorithms that do without this data. Also, most cars comply brilliantly with smart charging, no issue at all. But there are some cars which do not respond at all. That's relatively easy because you can quickly recognize that the car is not listening to smart charging and you just forget about it. And the hardest parts are some cars that sometimes don't listen to this. So we were in discussion with car manufacturers about this, but of course they will say it's a charger. It's very hard to get through. So this is very challenging. What do you do with a car that mostly complies and sometimes doesn't? And then some cars are on timers, which tricked us in the beginning. Because we assumed, well, we allowed those cars to charge, but they were actually on a timer because they wanted to make use of the economy 7 tariff. So we said, well, this car can charge, it isn't charging, so we'll assume it's full. And then we put it in a low priority, and when the low tariff kicked in, we said, no, you cannot charge because you're already full. So this was also a learning that we had to take into account to solve for. Even harder are network failures, which actually tend to happen a lot in the UK. We found out especially with a GPRS connection, it's not very stable. And you cannot allow, even in the case of a a connection failure, you cannot allow an overload. So you need to have backup scenarios for everything that can go wrong. It's very often the communication between the charger and the backend. But of course, also our backend might go down. Fortunately, it hasn't happened, but it could happen, and we need to be able to cope with that. The charger itself can go broken. The car might not respond to the smart charging signals. You have to have backup signals for everything, backup system. Very important, also very often forgotten, is that data costs are not for free. There's also read a lot of papers which send new smart charging signals to chargers every few seconds. If you do this, then the data cost will go up to 10, 15 pounds a month per charger, and this will ruin any business case. To give an idea, we have to stick below 6 megabytes per charging station per month. So this is really limited amount of data, and this makes the algorithms that you need quite complex because you have to do with very limited steering signals. And also the bandwidth is limited because usually you connect charging stations via GPRS because it has the best coverage, but also the lowest bandwidth. So these are practical limitations that make smart charging quite complicated. Then skipping to the learnings. So I have 6 learnings here. The first of all, and this is by far the most important learning, is, well, one, that is technically feasible, but even more important, that it's acceptable to the majority of the participants. We actually got some very interesting results. The very large majority of people that were asked, and this was well, several hundred people that replied to this, so that this has statistical relevance, scored an 8, 9, or even 10 on the question, how satisfied are you on a scale from 1 to 10 with the smart charging, the load management. And we got, well, ridiculously high responses, which actually surprised me because I was a project manager. I was dealing with everything that was going wrong. So I had a completely different perception. I thought everything is going wrong. But of course, I only dealt with the problems. I'm not surprised with the 3 to 6% that gave a low score because, well, this was a project, things went wrong. I was personally responsible for, I just made an error in our system and 50 cars were not able to charge at all overnight. This is a real issue. There were some chargers with a broken display. We sent out new chargers and the display was broken again. Well, people are not happy if this happens. But still, a lot of people said this is completely fine, and actually very fine. We appreciate it very much, which is great news. If this would have been the other way around, we could stop smart charging. And well, what Miriam introduced, thinking about legislation would not be necessary because people don't accept this, then you're done. But fortunately, it's completely the other way around. People are very okay with smart charging, and this is great. Second one, well, there's a lot of data coming from this, and it's very, very, very valuable information, which can be used for a lot of new scenario plannings in the UK or anywhere in the world. And it also shows that, as we expected, there is a lot of flexibility in electric vehicles. We looked up the figures for the UK. In Britain, there are currently 40 million cars. Let's assume they will all be electrified at one point and they all charge at 7 kilowatts. And we're talking about 280 gigawatts. to put that in perspective, the average power consumption is 35 gigawatts. So that's 280 versus 35. So that's a huge, huge potential. Of course, not all cars charge at the same time, but if you would only be able to use 10% of this flexibility, then we're talking about 28 gigawatts of pure flexibility at a marginal cost of nearly nothing, because people are completely fine with this. And the chargers are already there, and all it takes is 6 megabytes of data every month. So there's a huge business case there. And actually this is, I started with our mission and our vision that we want to charge all cars on renewable energy. And this is how to do it, because you cannot have a lot of renewable energy in the energy system if you're not able to have the demand follow the supply. And there is no demand that is as flexible as 7 million cars which do smart charging. This is how you can stabilize the energy system with renewable energy in it. So this is great news. Third learning, and this is also very, very important. You need to inform people what is going on with smart charging, and they need influence. If you don't, people know that smart charging is going on, but they don't know what it does, then whatever is going wrong with the charging station is due to smart charging. People have a pebble in their plug and they plug it in, but due to this pebble, it cannot completely plug in. Well, that must be smart charging. They use an invalid RFID card, it must be smart charging. The circuit breaker tripped for some reason, must be smart charging. And as soon as you take that away and you inform people of what's going on, then they're completely fine with it. Also, well, we learned from the other technical party, it needs to be easy. If you don't make it easy, people will not use it. And you also need to empower people a little bit that they can press this high priority button, that they have the feeling that they influence. The interesting thing is, they hardly ever use this. I didn't put in this data because it would be too long. You can find it in the reports. I'll show the links at the end of the presentation. In the beginning, everybody uses this button. Everybody wants to try it out. Everyone wants to be certain. Then they forget it, and they find out that they don't actually need it because the car is charged. And then we very quickly see that well, in the majority of sessions, if the button is pushed for high priority, then they actually need it. Because the facts, and this is also important, the fact that they have to take out their phone, open the app, it only takes a few seconds and have to push the button, is penalty enough not to do it if you don't need it. And this is also very interesting. So there was no penalty on pressing the high priority. The fact that they had to push it was penalty enough. And we can see that from the data analytics that people don't, well, except for some cases, but they don't misuse this function. So this is also what we did. This is our own white label app, which we provide to our customers. And it's used for finding chargers for roaming and paying, but very important also smart charging. You see it here on the right. I'm not sure if you can see my mouse, but there's a prime button there. Actually, this is an old layout. We just uploaded a new one. It's called Charge Assist. You can just download it from the Play Store. Where on charging stations connected to the GreenFlux platform, you can push this button, and this is the high priority button. So we took this learning and put it into our offering. Fourth one is a very interesting one. So this was from the third iteration where we introduced this time of use tariff. It's highly effective and also very dangerous. So these are the results. So these orange, what you see here, these bars are the moments that the transaction started. So these orange ones are the normal distribution. So you see a lot of people that come home in the evening, 5 or 6 o'clock, and they start a transaction. And then this decays overnight. And the blue ones are the start of transaction in the trial 3, where we see a huge peak at 10 o'clock, which, as you might remember, is when the low tariff kicked in. Also, if you look at the energy consumption here, you see the energy peak at noon, at 6 o'clock. From 6 to 9 is completely shifted to 10 o'clock in the evening. This may not seem like a big shift, but remember that the household peak is also there at 6 o'clock. So we shift all this consumption to a later stage. So this is a huge success for the grid operator. However, for the energy supplier, this is not so good. Because imagine, well, 40 million cars, let's say in 5, 6 years in the UK, we have 5 million electric cars. imagine doing this with 5 million electric cars, and there's a sudden increase of 35 gigawatts at 10 o'clock in the evening. This will for sure cause a blackout in the UK, because there's no way that the energy system can suddenly deliver 35 gigawatts of power. So the good news is, it's with a very easy incentive, you can have a huge result. The caution is, be very, very aware what incentive you give. And personally, I can go into much more detail, but I would need more time. Personally, I don't believe that dynamic energy tariffs applied directly to end users will ever work because of this effect. So what I think you should do, and what we are currently offering, so we have the GreenFlux platform, we take into account the grid limitations, and within this grid limitations, we can do energy optimization. So we have a connection to the energy supplier or the balance responsible party who is connected to the wholesale market. And we take input from them via the Open Smart Charging Protocol or Open ADR or custom API, doesn't really matter. They tell us how they want the group of electric vehicles to be charged based on their wholesale position. And the incentive to the end user should not be a dynamic energy tariff, because we can get the effect that everybody starts charging at the same time. But it's probably much more robust to just give the end user a fixed discount or free charger, or have them save for towels or whatever. But no, basically buy their flexibility for long term. So just in a fixed count, maybe give them 1 pence of discounts per kilowatt hour anyway. There's different ways to do that. Fifth, learning. I showed you a lot of graphs with blocks stacked to each other, and these were 15 minutes blocks. This was our old algorithm, but we couldn't change it halfway the project. Where we just collected all the data, all the inputs, and then collected it up to the next 15-minute block, and then calculated a new profile. This is not ideal. For instance, if somebody did a high priority request, we would say, yes, thank you, it will become active within 15 minutes. Well, this is not what you would expect if you press a high priority button. Also, when somebody started a new session, it could take up to 15 minutes before the car actually started charging, because we needed to wait for the next calculation run, whether or not this was possible. So we started with this system, 15 minute blocks. And what we've now switched to is a completely event-based algorithm, which looks a bit more challenging. And it actually is a lot more challenging, because if all events can occur at any given time and you have all parallel processing, this is a nightmare for our developers, but we've cracked it. And as you can see, it becomes more interesting. Our developers call this smart. But the good thing is, with this, we can now directly respond to events, offering much more versatile solutions. So the easy things are, whenever a session starts or stops, we can react to that. When EVs are nearly full or full, we respond directly to high priorities requests, either from a driver or a charger. But also do more smart grid integrations, like put DC charging stations in the same network as AC chargers, or when there's a sudden change in available capacity from a grid operator, maybe a power line went down and the power needs to ramp down immediately within a second. So the scenarios that we can support become much more interesting, also towards the transmission system operator or the balance responsible parties. So this is a learning that we took that was very important, but not that easy also. And maybe the most important one is the technology is ready. And again, Miriam mentioned at the beginning of this webinar that the UK is looking into legislation. That's a tricky part. Also, that I could talk for a long time about, but then it would take up too much time. But the technology is not the issue. We can apply this. We can use OSPP. 2.0 is fine, it's nice, but version 1.6 already suffices, which is supported by the vast majority of charging stations. And it's there. And if we go back at these 4 reasons why you would do smart charging, which I started with, well, this is quite simple. So we take a building, we measure what's going on there, whether there's local production or what the building is doing, and we'll take that input. We take the user input via an app. The energy supplier input is, as I mentioned, via OSCP or OpenADR or a custom API, and the same goes for the grid operator. And we turn that into smart signals to, well, this shows only 1 charger, but to a bunch of chargers. And the technology is no longer the issue. And the customers that we already have can already make use of this technology. To finish, so what we did not stop after this, so we'll continuously update our algorithms, do further integration with apps, with third-party apps, metering platforms, testing charging stations, and we are currently rolling this out commercially. So this has been a very good project for us. We learned a lot, and that's it. So these are my contact details. Please also visit those links over there. Oh, I see this is a typo. They're both project summary. Actually, the top one is the project results. This is a lengthy report of 591 pages. So take the time to go through that, but every detail is there. If you're really interested, please read this because it's very, very, very interesting information. If you have less time, then the project summary is 32 pages. Also very interesting. I think this was it.